limit as x approaches 1 from x squared plus 5x minus 6 divided by x squared minus 1. Okay, so we have a different rule for limits of rational functions. So note, if this number, right, we know x approaches a, if a is in the domain of f of x, do the same thing. Plug it in. If it's not in the domain, then we have to discuss other options here. If a is not in the domain, then, and I'll explain in a minute, so let's come back. So it's the same rule applies if this number is in the domain of this function. If this number is not in the domain of this function, I cannot apply this rule. Just plug it in. I cannot. So what happens then? I'll come back to the problem. What happens then? So what will happen if a is not in the domain? I will get a number not 0 over 0. So I'll put it in parentheses, not 0 over 0. I'm not discussing 0 over 0. I'm discussing a number over 0. A number over 0 has three possibilities. Either infinity, or negative infinity, or of course DNE. If we have 0 over 0, now I'm discussing 0 over 0. So in other words here, as you notice, infinity, negative infinity, DNE, it means the limit does not exist. How come? Well, infinity is not a number. And at the beginning, when we started limits, we said it has to be a number, not infinity, or negative infinity, or DNE. So if I have a number over 0, this is done, is dead. The limit will not exist. But the answer has to be either infinity or negative infinity or DNE. However, this situation has hope. What does that mean? It could still be DNE or does not exist, but it has potential. It may exist. When we say it has hope, there is no guarantee. We are only saying it may exist. So this is a very important classification. A number over 0, no hope. None. No hope. And you have to look for these answers. Only one. Not this and this and this. No. Either this or this or this. If the initial situation is 0 over 0, I'm not saying the limit exists. I'm only saying it is possible. But this one is closed. Done. The limit will not exist, and you have to look for one of these three. Okay, finally, let's go back to the problem. We have to plug it in to see if it's this, and then I look for these three, one of these three answers, or if it's this, and I can continue. So, can anyone plug in 1 and tell me the numerator? What is the value of the numerator and what is the value of the denominator? When we plug in 1.
It's going to be 0 over 0.
Brilliant. Who was that? Yulia?
Yeah.
Thank you. Perfect. So, I'm happy. Why? Because I have this situation. The limit may exist. It's not this dead one. where the limit will never exist. Awesome. So I'm going to copy it again because I don't have room here. And let's factor the numerator and the denominator. So I'm going to copy the problem one more time here because I don't have enough room. So x squared plus 5x minus 6 over x squared minus 1. Do not drop the limit operator. We have not applied it yet. So can anyone factor the numerator for us?
X plus 1, x minus 6.
Careful, the sum. So this is the sum, and this is the product. So
x minus 1, x plus 6.
Excellent. X minus 1, x plus 6. Perfect. Can anyone factor the denominator? And we discussed this at the beginning of the class. It's one of those.
X minus 1 and x plus 1.
Brilliant. Thank you very much. Who was that? Thank you. Good. Do you notice anything? Can we get rid of anything?
We can get rid of x minus 1.
Excellent. Good. Do not drop the limit operator. Limit as x approaches 1 from x plus 6 over x plus 1. Can anyone now plug it in and give me the final answer?
Divided by 2.
Brilliant. That's it. See, this is the only time when the limit operator disappears. I applied it. I was asked, what is the trend of this function when x gets closer to 1? And Sandy did this. He said 1 plus 6 is 7, 1 plus 1 is 2. Done. Does the limit exist? Yes. It's a number. And we had this situation. Okay. Any questions before we continue?
So when we did a factor, we were looking for a trend, right?
Yes. So once we factored, we realized that this factor goes away. It does go away because it creates the 0 over 0. The x minus 1 creates the 0 over 0. Once I removed that situation, the 0 over 0, I had only x plus 6 over x plus 1. So now the limit of this is 7/2. But I have to simplify it first. If I don't simplify it, I still get 0 over 0. Once it goes away, the limit exists and it's 7/2. Is that okay?
Yes.
Perfect. Okay. Good. I will also like to look at some one of these infinities one, which I need to explain. But I want to make one up before we choose the infinity ones when x approaches infinity. Okay, allow me to make one up. What if I have the limit as x approaches 5 from the right of 1 over x minus 5? It's a rational function. In order to determine what's going on here, I have to plug it in. And you can say, well, why do you have to plug it in? Because I need to know, especially in a rational function, I need to know if it's this or this. Because if it's this, I will look for one of these three answers. If it's this, I'll factor, I'll simplify, whatever. So can anyone tell us what is the preliminary? When you plug it in, what do you have here at the top and the denominator?
1 over 0.
1 over 0. So that's what I wanted. That's why I created this example. So it's this situation. And I have to choose now. Either positive infinity or negative infinity or d/n/e. Only one of these three. Okay. So here's how we do it. 5 from the right, remember what we said, if this is 5, 5 from the right will be with numbers larger than 5. So give me a number very, very close to 5, but larger than 5.
5.5.
Excellent. 5.5 minus 5, just give me the sign of the answer. I don't care for the exact answer. I only care about the sign.
Positive.
Good. That means that I will choose which of these options, knowing that the top is positive 1 and the denominator will be a positive number. What will I choose from these three?
Positive infinity.
That's it. That's it. Excellent. Any questions on this?
Wait, how do you determine it's a positive 0? Can you do that one more time?
Sure. 5 from the right. Can you give me a number close to 5 from the right of 5?
Two.
The 2 is not to the right of 5. 2 is right here.
Oh, 6.
Closer. I need closer. 6 is far. 5 point?
5.
Good, 5.5. 5.5 minus 5. I only need the sign of 5.5 minus 5.
Okay. Okay, I see.
So since it's positive, and it happens that the numerator is positive, that's why I get a positive number. What if I change the problem and say this? X approaches 5 from the right, negative 1 over x minus 5. What will you say now?
It doesn't exist.
So we plug it in.
Negative infinity.
Exactly. We have negative infinity over 0. We can never choose it does not exist before we decide if it's one or the other. We cannot, you can say, but the limit does not exist. I agree. For all these limits, you can write DNE, but you have to write positive infinity if it's positive infinity. It's a type of DNE, but it's positive infinity and negative infinity. And then that will be the last option. And I will give you an example in a minute. Only when both sides go to different things will be DNE. But we only have one side, although that can happen too, even for one side. So the numerator is negative, the denominator is positive, as we just discussed, so then the answer will be negative infinity. Now, here's my next question. What about the limit as x approaches 5 from either side of 1 over x minus 5? What will you answer now?
Does not exist.
Of course. What does that mean? So it means that at x equals 5, if you remember from the college algebra, there is a vertical asymptote at 5, which means from the right, the function goes to infinity, but from yeah, so I changed the function. Sorry. I meant to write the same function, but everything is okay. It's DNE anyway. But from the other side, it's negative infinity. So one side goes to positive infinity, the other side goes to negative infinity. That's why this is DNE. Okay, so let's go back and share. And I wanted to show an example with when x approaches infinity. So let's choose one here. Let's say 35. Still a rational function. Limit as x approaches infinity. X squared plus 2x plus 3 divided by 3x squared plus 5. Okay, so this is a different situation. It's still a rational function. But what is different now? This. We have never seen this before. as x approaches infinity or negative infinity. So that's why this example is different. Okay. So I want to refresh your memory for 1 minute, 1 second, about a function that we looked at last time. And I said, please remember this function, 1 over x. If I ask you now, before we even look at this problem, which appears to be more sophisticated. So let's discuss this. Limit as x approaches infinity from 1 over x. Don't say anything just yet. I'm showing approaching infinity. Let's say x approaches infinity with red and the function with blue. So x approaches infinity. Where is the function going?
Towards zero.
Thank you very much. Perfect. Limit as x approaches negative infinity from 1 over x. X is with red, function is with blue.
It's also go to 0.
Exactly. Good. Let's analyze this situation. In college algebra, I show my students a very simple explanation for this. If the degree of the top, which is, can anyone give us the degree for this?
Squared?
Yes, degree 2. And can anyone give us a degree for this?
2.
Yes. So in college algebra, we only say this. If the top and the bottom have the same degree and the limit approaches infinity or negative infinity, the answer is always the leading coefficient over the leading coefficient. This is what we quickly show our students in college algebra when we graph rational functions. Well, here I want to show you why. Can you still use this concept? Yes.